Hello and welcome, class, to another lecture in Chapter 9 of Burge and Overby's Chemistry Atoms First, where in our previous lecture we introduced what an aqueous solution is, how we can measure concentrations of ions or particles inside of your solution. And what we're going to be doing today then is discussing whether or not your molecules or ions are going to dissolve in the first place, and as well as if you're mixing solutions of these ions or molecules together, will you see a chemical reaction? And specifically, we are going to be talking about precipitation reactions today. All right, well, the definition of solubility pertains to whether or not your thing will dissolve in water in the first place. Solubility is the maximum amount, maximum is the emphasis here, maximum amount of solute that will dissolve in a given quantity of solvent. So sometimes you have a little bit of stuff and it will dissolve. If you add too much, it can't because you're running out of space in your water. But what's important to recognize here is that not every compound will dissolve or dissociate. For example, in the right, what we have illustrated in this beaker is sand. Obviously, sand does not dissolve in water. It's why when you go swimming in the lakes or oceans or rivers, you have something beneath your feet. Sand, silt, clay, dirt, these things do not dissolve. They are not soluble. And because they are not soluble, they're just gonna sit there. Right, so just because you place something in water, particularly if you're working with a chemical reaction or you're writing out a chemical equation, just because you write something like sand in water turns to sand aqueous, implying that with this phase of aqueous it has dissolved, experimentally we would see that this is not true and this equation is nonsense. Like, just because you write something on paper doesn't necessarily mean it's going to happen in reality. So, how can we tell which compounds are going to dissolve and which will not? And we will primarily be focusing on the process of dissolving, aka we will be focusing on ionic compounds today. We'll be focusing more on sugars and molecular compounds and how they dissolve a little bit later, basically in the spring. However, a good rule of thumb, again, goes back to what we've talked about with intermolecular forces, like dissolves like. If you are working with a polar molecule, chances are it will dissociate in water. If you're working with a nonpolar molecule, like oil, chances are it is not going to dissociate in water. All right, but the ionic things are the things that are a little bit tricky, so let's talk about those. All right, well, as has been the case throughout this semester, and hopefully you are used to it at this point, we have a series of rules to help guide us when we're trying to figure out whether or not something will or will not dissolve. These rules we call the solubility rules. So there are three big rules in the solubility rules, and the first is what we can see here. The following ions are always soluble. So if your ionic compound contains lithium, sodium, potassium, rubidium, cesium, ammonium, nitrate, acetate, or chlorate, it will be soluble. So for example, if we were to write out or predict whether or not lithium sulfate will dissolve in water, the way that we determine this, at least with the first rule we have seen so far, so we write out the chemical formula for lithium sulfate, 2 lithiums with a plus charge for every sulfate that has a 2 minus charge in solid form, add it to water, and what we will have to ask then is, will this thing dissolve? If it does not dissolve, we see no reaction. If it does dissolve, we will see the lithium and the sulfate separate. So if your ionic compound contains something that is on the always soluble list, it will dissolve for sure. So because lithium sulfate contains lithium, which is on the always soluble list, it doesn't matter what sulfate's nature is or what sulfate wants. Lithium wants to get away. Lithium is so stable interacting with water that it is going to break apart from the sulfate, giving us 2 lithiums with a plus charge and a single sulfate with a 2- charge, both with a phase of aqueous, meaning that they are dissolved. All right, so a pattern to see with the ions on the always soluble list. This pattern is going to help us a little bit, at least in terms of identifying in a straightforward way which things give us soluble compounds. The first 5 ions listed are the alkali metals, specifically because they are in ionic form. These are the alkali metal ions. So lithium, sodium, potassium, rubidium, and cesium are all in the first column of the periodic table, and periodic trend would also dictate that francium would be in this list as well if there was enough of it on this planet to actually gather and put into an ionic compound. All right, francium is super radioactive and not very abundant as a result, so francium's not technically on this list, though we could assume that it would be. All right, the next 2 ions both start with an N. They're not the only polyatomic ions with an N present, but they are the most commonly occurring polyatomic ions that have an N, ammonium as well as nitrate. And the last 2, the acetate and the chlorate, are a little bit rarer. Like, we don't see them in compounds, at least commonly at the general chemistry level. Sodium acetate is the most common acetate form, but other than that, we don't see it too much. But assuredly, again, these are going to have to be ions that we know and recognize as being always soluble. All right, the next rule in our list of solubility rules states that the following ions are mostly soluble. So solubility exists on a spectrum. It's not really a binary whether or not something will or will not dissolve, specifically because there's a temperature dependence involved. If you change the temperature, you can definitely get something that is soluble to become insoluble or insoluble to become soluble. What we are assuming in this conversation is that we are working at room temperature. The things on our always soluble list, as a result, will always be soluble. In addition, the following 4 ions will also be soluble, provided that they are not bonded to the ions in red below. If the ions are coupled with the things in red, these cations in red, they will make exceptional insoluble compounds. So for example, if we were observing sodium chloride versus silver chloride, sodium is one of those always soluble ions. Chlorine is one of those mostly soluble ions, and so we would assume that sodium chloride is going to dissolve. Silver chloride, on the other hand, we don't really know what's up with silver. It's not on the always soluble list, so we will start with the chlorine. This is, again, a mostly soluble compound, so the way that we double check whether or not this thing will dissolve is we check in these 2 bullet point areas here where chlorine is. We can see it present right where I have circled. And what this list means is that if chlorine is bound to silver, mercury 2, or lead, it will become insoluble. It will not be able to dissolve. Well, sure enough, silver is right here on the list. So what this means is that the coupling of silver chloride actually turns out to be not soluble, which in parentheses is the definition of insoluble. So because silver chloride is not soluble according to these solubility rules, if we were to sprinkle some in a glass of water, it would sink to the bottom just like sand does in the glass. So we can see that bromine and iodide are also on this list, just to again observe a pattern. The halogens are here and present, at least the halogens aside from fluorine. Each of these halogens characteristically behaves the same way. If they come into contact with silver, mercury 2, or lead, they will become insoluble. They will not break down in solution. However, with any other cation, just like the sodium chloride case, we would assume that it is going to be soluble. So something, for instance, like barium chloride. Since barium was not on the always soluble list, we're going to have to observe chlorine to figure out whether or not this compound would break down in water. With chlorine, again, we have to double check what is listed after it on this bullet point list, because barium is different than silver, it's different than mercury, and it's different than lead. We would actually assume that the soluble nature of chlorine here takes over. We would expect to see barium 2+ as a result, and 2 chlorines with a minus. All right, so this is how we can use the except insoluble rule down below. If the ion, specifically the cation listed, is not on that exceptional list, the chlorine is going to take over, which is mostly soluble, and we will see the barium chloride in this specific example break up. All right, and sulfate is also listed down below. Sulfate has its own list of cations that it becomes insoluble when it comes into contact with. The first 3 are the exact same as the chlorine, bromine, and iodide. We can see silver, mercury 2, and lead being present here. However, there are 3 additional ions present: calcium 2+, strontium 2+, and barium 2+. Now this means if we were to take barium and couple it with sulfate, it would behave differently than when we coupled it with chloride. Because barium sulfate, when added to water, or I should say because barium is coupled to the sulfate in this case when we add it to water, barium is on this list of complexes or ions that become insoluble when bound to sulfate. This means that when added to water, we would see no reaction. Just like the silver chloride, barium sulfate is expected to remain insoluble and will just exist as a solid in water, just like sand. It's just going to sink to the bottom and hang out there and not dissolve at all. All right, our last set of rules, our last rule, I guess, in the set of rules pertain to ions that are mostly insoluble. These are ions that we default into assuming that they are insoluble. So if you see carbonate, phosphate, chromate, sulfide, or hydroxide as an anion in some type of ionic compound, we assume that these things are insoluble. We assume that they are not going to break up, that they are going to remain as a solid in water. Now, just like with the previous mostly soluble compounds, there was a list of exceptions. Here with the mostly insoluble compounds, we can see that there is also a list of exceptions, but it is a very small list. These mostly insoluble compounds will end up being soluble when they are coupled with the always soluble ions previously listed. So for example, sodium 3-phosphate or sodium phosphate. As a solid, when added to water, we would have to ask ourselves again, according to these rules, will the thing dissolve? Phosphate is on the mostly insoluble list. However, sodium, again, will always be soluble. And always is more persistent than mostly, right? In some type of logical argument, always is going to always win. Always will always be the case. So because sodium is always soluble, it will dominate in terms of chemical characteristic. The sodiums will assuredly break apart from the phosphate. Even if the phosphate doesn't want them to, the sodiums are like, nah man, I'm out of here. And they're gonna go hang out with their friends, the water molecules. Well, phosphate is just left to struggle a little bit unstable, but still relatively stable because of the presence of water. All right, the other exception for solubility is specifically with the hydroxide. Hydroxide will be soluble if it is coupled with the barium 2+ ion, but that is the only additional exception. if the hydroxide ion is bound to anything else that is not on the always soluble list, we will assume that it is going to exist as an insoluble solid. So barium hydroxide, we would expect to break down into the barium and hydroxide ions. However, something like calcium hydroxide, because the calcium is not on this list of exceptions, because calcium is not an always soluble ion, we would assume that this in its solid state, when added to water, would just remain in its solid state. We would see no dissolution, we would see no reaction. Calcium hydroxide would just, again, float or softly fall to the bottom of your beaker or your glass or whatever, and you would not see any dissolution occur. All right, so in review, we have the always soluble ions that when present in some ionic compound will assuredly dissolve no matter what. We have the mostly soluble compounds, which our default is that they will dissolve, except with the small list of exceptions. And here, last but not least, we have the mostly insoluble compounds, which we default onto assuming that they are not going to dissolve, with rare exception. All right, so I would like you guys to spend a moment to determine whether or not the following compounds are going to be soluble or insoluble. If you pause the video, please also be aware that you're totally free to go back and look at the previous soluble versus insoluble rules. If you are in my class specifically, these are not rules that I will expect you to memorize. I will supply these solubility rules on the final exam, or you will have the total freedom to use them on any homework assignment that you have coming up. So you're always going to be able to see those rules. There is going to be no need to memorize them. All right, welcome back. So let's identify whether or not the following ionic compounds are going to be soluble or insoluble when added to water. And before identifying, that's a really important thing that I should probably clarify, is that the solubility rules specifically pertain to aqueous solutions, ones in which water is the solvent. There will be different solubility rules when we are working with different solvents, and we're going to get more into that in the spring semester. All right, so let's turn our attention to the 6 compounds below. First, we are working with calcium chloride. Since calcium is not on the always soluble cation list, we must turn our attention to the chloride, which chloride is one of those mostly soluble ions. Because it is mostly soluble, we must double check to see whether or not calcium is on the exceptional list. And if we do so, I'm just going to clean this up a little bit, we can see that calcium is not on the exceptional list. Not for chloride, at least. What this means is that calcium chloride is going to be soluble. It will default onto the default for chlorine's nature. This will be a soluble compound. All right, next we have sodium oxide. And our first question should always be, is one of the ions present on that always soluble list? And in this case, we can see, yes, the sodium is one of those, again, always soluble ions, meaning that our sodium oxide is also going to be soluble. It doesn't matter what the oxygen's nature in terms of solubility is, the sodium will win. It is always soluble. All right, next we have iron sulfate. Now, iron was not on the always soluble list. In fact, it hasn't been mentioned yet, so we are going to default onto looking at our sulfate here. Now, the sulfate, just like the chlorine, was on the mostly soluble list. And if we go back to that mostly insoluble list, we can check out to see if the iron is on the list of exceptional ions present, and it is not. What this means is that, just like with our first example, we will default onto observing sulfate as being mostly soluble, and iron sulfate will, as a result, be labeled as soluble. All right, next we have another sulfate ion present. This is lead sulfate. Now lead sulfate, we are going to break down just as we have in the first 3 examples. Lead is not present on the always soluble list, and sulfate, again, is identified as being mostly soluble. So we have to observe whether or not lead is on that mostly, or if it's on the exceptional list for the mostly soluble ions, and sure enough, lead is right here. This means that even though sulfate is mostly soluble, this is going to be an exceptional case where the compound is going to be insoluble. Our lead sulfate will not dissolve. It is insoluble by definition. All right, copper sulfide. Here we have another example of a cation that is not on the always soluble list, so we must observe what sulfide's kind of default nature is. Now sulfide was introduced, to clear this up again, on the mostly insoluble list. This means by default we will assume it's going to be insoluble unless there is something presented on our exceptional list that is also in our compound. Well, sulfide, according to this, can only be soluble if it's coupled with one of those always soluble ions, of which copper is not. So because copper is not an always soluble ion, sulfide, which is mostly insoluble, will dominate and cause copper sulfide to be an insoluble compound. All right, and last but not least, we have ammonium chloride, where here we have another example of one of the always soluble ions popping up, and it's even being partnered with something that is mostly soluble. There is no exception in this case. Our ammonium chloride is assuredly going to be one of the soluble compounds. If we sprinkle some into water, we will watch it slowly disappear. All right, so if you have any questions on these soluble or insoluble identifications, please shoot me an email if you're in my class, or if not, feel free to leave a comment down below and we can hash it out in the comments section. Well, now that we have under our belts the means with which to identify whether or not certain compounds are going to dissolve in water, let's talk about mixing those solutions together. Now, if you mix 2 solutions together in which one of the products is identified as an insoluble solid, we call that insoluble solid a precipitate. So a precipitation reaction is one in which a precipitate is created. An insoluble solid is going to form upon the mixing of 2 aqueous solutions. Now in the picture down below, we have some examples of precipitate reaction products, where in each of these cases, we can see that the test tube is cloudy. Cloudy observations in test tubes are always a sign of a solid forming, aka a precipitate is forming. So if you mix 2 solutions together that previously were clear, they might have had some color to them, afterwards you see a cloudy solution forming, this means that you have created some type of insoluble precipitate, regardless of what the color of that solid might be. All right, so let's talk about how to identify precipitates when they occur. We are going to do so by working through an example, because what is a better way to learn than by doing? So let's write the balanced molecular equation that occurs from the mixing of the following 2 reactants. And our hint here is we are going to assume that there is a double displacement reaction. Our question is, does the reaction result in a precipitate? So here we are being told that we are mixing together 1 solution of potassium sulfate, which is aqueous. Again, anytime we see aqueous, what this means is that your ionic formula that is listed here is dissolved. It is separated by the water molecules. So potassium sulfate is soluble, it will be dissolved, creating a clear colorless solution. Similarly, strontium nitrate is listed as being aqueous, which means it is also dissolved. It is also going to exist in solution as a clear and colorless solution. The question is, what happens when we mix these two things together? Well, we are told that there is a double displacement reaction, and this double displacement reaction is going to result in the swapping of either the cations or the anions. It doesn't really matter which one you pick. I tend to go with the swapping of the cations because they are listed first. So we are going to swap the strontium for the potassium in each of these compounds and hypothetically list both of these things as our products. Now, we're not going to include a phase label at first because that's what we are in charge of trying to figure out, as well as we are going to have to write the stoichiometric coefficients when necessary to balance this hypothetical equation. So when potassium and nitrate come together, this is going to be the first of our swaps. Potassium has a +1 charge, nitrate has a -1 charge. What this tells us is that we only need one of each to create a balanced or charge neutral complex. So I'm just going to erase those charges up on top. There are no need for additional subscripts. And in parentheses, I'm going to leave a blank here. And I'm going to write the other product kind of down below to make sure I have space for everything. The other partnership that results from the swapping of our cations is strontium sulfate. Strontium has a 2+ charge according to its electron configuration, and sulfate, by definition, has a 2- charge. So what this tells us is we only need 1 strontium per every 1 sulfate to create a charge-neutral compound, so there is no need for any additional subscripts here either. Parenthesis, phase, parenthesis. So before identifying phases, let's balance the equation first. So on the left-hand side of the equation, we can see we have two potassiums as well as 2 nitrates. On the right side of the equation, we see currently we only have 1 potassium and 1 nitrate. How fortunate that they are coupled together in one compound. It makes balancing this equation really easy. All we need to do is include a single coefficient of 2 out in front. So remember, just because coefficients are listed in an unbalanced equation as you are writing out your products, this does not mean that you have to slap those same subscripts into the compound on the product side. You always want to create charge-neutral compounds first and balance these subscripts with stoichiometric coefficients like this 2 out in front. So here we can see that we have a balanced chemical equation. All of the atom types are equivalent on each side. 2 potassiums, 2 nitrates, 1 strontium, and 1 sulfate. So now we can identify whether or not these things are soluble or not. This is going to tell us what the phase on our product is going to be. So potassium nitrate, let's pay attention to this first. And in fact, I'll even change colors just to make this a little bit easier to see. I'll swap to blue. So potassium, we will identify as whether or not this is on our previous lists for the solubility rules. And sure enough, potassium, if you go back, is on our always soluble list. Potassium is right here. This means that no matter what the potassium is bound to, this compound will dissolve in water assuredly. And in fact, while we're here, the anion that is present in this complex is nitrate. So this compound is really going to dissolve in water. There's nothing stopping it. Both the potassium and the nitrate are always going to be soluble. So when we come forward to our chemical equation here, we're going to signify that this compound is soluble by including an AQ phase after it in the balanced chemical equation. This tells the reader that potassium nitrate is soluble and will break up or dissolve when placed in water. So let's do the same thing, take the same approach for our strontium sulfate. So strontium, we have to ask ourselves if it's on the list of always soluble ions. So let's just go back and look. Here. And going from left to right, we can see that there's no strontium present here. So since strontium is not on the list of always soluble things, let's pay attention to the anion present. Now this anion, we are going to have to check if it's on the mostly soluble or mostly insoluble list. So we'll just start with the mostly soluble and, oh, look, there it is. Sulfate, right here. So strontium sulfate could be soluble provided that strontium is not on the list of exceptional insoluble cases down below, and, well, there it is. So because when strontium is partnered with sulfate, we have an exceptional insoluble case, this means that our strontium sulfate in this chemical equation is going to be insoluble. Because strontium sulfate is an insoluble compound, when you mix potassium sulfate and strontium nitrate together, you will create a precipitate. You will create solid strontium sulfate. So anytime you're working with a reaction and you find that one of your products is insoluble, like this strontium sulfate here, we are going to label again to the reader that it is insoluble by including the phase S for solid. This means that it is not soluble, it will not dissolve, it is going to exist in solid phase. All right, so we can take this same approach when trying to identify products, regardless of the reaction. If you don't know whether or not you're working necessarily with a precipitation reaction, list out your products as we did here, balance your equation as you normally would, and then take a break to identify whether or not your cations and anions are on the solubility list somewhere. If you're working with something soluble, you're going to add an AQ for phase. If you are working with something insoluble, you will add an S for solid. All right, so this brings us to our need to, let's say, redefine our chemical equation notation a little bit. So the form of the equation that we just wrote, I had identified in the wording of the problem as a molecular chemical equation. Now, a molecular chemical equation does not necessarily mean that you're working with molecules as opposed to ions. A molecular chemical formula just means that all of your chemical formula are written as cohesive formula, that your compounds are being like what are described here. This is going to be different than the two additional forms of chemical equations that we're going to introduce here, the first being the total ionic equation. The way that a total ionic equation is written is going to look different than our generic molecular chemical formula that we're used to. In a total ionic equation, your chemical equation is rewritten to indicate which species are present specifically as ions in solution. So for example, the molecular chemical formula, I just totally realized I didn't finish writing that word. Our molecular chemical formula written below is for the combination of silver nitrate and sodium chloride, which creates silver chloride as a solid and sodium nitrate in aqueous form. So again, this is not the total ionic equation. This is the molecular chemical formula equation. So how we are going to approach rewriting this into the total ionic form, we're going to use the beakers down below to kind of illustrate what it is the total ionic equation is telling us. Well, silver nitrate, because we are told this is a soluble compound, means that the silver and the nitrate are going to be separated from each other when they're actually like in solution. So in this beaker, hypothetically, we would have a bunch of silver plus floating around, we'd have a bunch of NO3 minus floating around, but nothing would be bonded together. Each of these ions are separate. And similarly, in the sodium chloride beaker, which we are also told this is aqueous, this means that we'd have a bunch of sodium pluses floating around and a bunch of chloride minuses, but nothing would be bonded together here either. They would be in perfect ionic form. So we would rewrite in the total ionic equation form, representing the reactants that we're mixing together, the silver plus explicitly as a silver plus ion in aqueous phase, the nitrate with a minus charge in aqueous phase, the sodium plus as an ion in aqueous phase, and the chloride with a minus charge in aqueous phase. This total ionic representation of our chemical equation better represents the state of being for the ions inside of their separate containers. On the product side of our total ionic equation, we're going to take the same approach. We're going to separate the ions that are dissolved and keep the solids together. The reason why is if we observe this beaker on the right with our solid sodium chloride, the solid sodium chloride is solid. It is not separated into its ionic components dissolved in solution. Instead, we have a precipitate that is, or that would slowly settle to the bottom of this beaker. This is our silver chloride, and it is together in some type of ionic compound, not separated into ions. The sodium nitrate, on the other hand, is going to be separated because it's in aqueous phase, sodium plus, nitrate minus, say nitrate minus, sodium plus. We're just going to draw a bunch of them floating around. So the product side of our total ionic equation will explicitly list each of the compounds as they are found literally in this flask. Our our silver chloride would remain together in solid form because in the beaker it is still together in solid form. The sodium plus would be listed separately in aqueous form, and the nitrate with a minus charge would be explicitly listed separately in aqueous form. So the total ionic equation is a more expanded form of the molecular equation, which explicitly illustrates all of the chemical formula that are present kind of cohesively. So the advantage of the total ionic equation is that it is more accurate. It is a better representation of what is actually happening inside of your beakers. The disadvantage of working with your total ionic equation is that it is larger, it takes more time to write out, and it seems kind of almost like a waste of time when silver nitrate in aqueous form up above tells us the same information as down below, it's just not as explicitly written. So we have pros and cons on both sides, all depending on what problem you're working on. It may be more advantageous to use the molecular equation, or it may be more advantageous to use the total ionic equation. One useful aspect, though, of the total ionic equation is that we can explicitly see which species are chemically reacting versus which are doing nothing. We call this the net ionic equation. This form of a chemical equation is written specifically to indicate what is chemically reacting by removing spectator ions. And a spectator ion is an ion that appears on both sides of your chemical equation. This ion is present, in other words, on the reactant and the product side. Therefore, this signifies that they have not reacted chemically in any way. So if we go back to our total ionic equation, and I'm going to change colors back again for clarity here. No, misclicked. Red. And it's still working? Perfect. Okay, so we're going to pick out which ions are present in an explicit ionic aqueous form on both the left and the right-hand side. Well, sodium on the product side is listed as sodium plus, as well as it was found in this aqueous plus form on the left. Sure enough, in the equation itself, we see sodium plus aqueous on the left and sodium plus aqueous on the right. These we would call spectator ions, because they sit around in the stands watching the game be played, but they don't actually participate themselves. They are not active in the chemical reaction, they're just there watching it happen. The other spectator ion that is present is the nitrate in aqueous form. Similarly, we see that there is nitrate ion in aqueous form in the beaker on the product side as well as on the reactant side. And sure enough, in the total ionic equation, nitrate minus charge aqueous on the left, nitrate minus charge aqueous on the right. We would also label the nitrate as a spectator ion as a result. It does not change chemically, it's just physically there to provide charge balance. Therefore, the net ionic equation, in which the spectator ions are removed, is going to be everything left over in this total ionic equation that hasn't been crossed out. So the silver plus, the chloride minus, and the silver chloride on the product side, we would conclude are going to be the net ionic equation. Silver plus in aqueous form plus chloride minus in aqueous form turns into silver chloride as a solid. So yes, there is both silver and chloride on the left and right hand side of this equation. However, they were presented in different forms. On the left hand side, we see that we are working with aqueous ions. And on the product side, we are working with a solid. Something that now has a chemical bond that's holding these two ions together. It is chemically and fundamentally different than the aqueous ions that the species started as. So this would be the representation of the net ionic equation for the chemical equation, or the total ionic equation on the previous slide. And the last thing that I am going to introduce today, on top of talking about solubility, precipitation reactions, total ionic equations, and net ionic equations, is how we measure it. So in part 1's lecture, we talked about concentration and using stoichiometry to kind of manipulate some measurements for how many things are present in solution. Building off of that, we are going to introduce what is known as gravimetric analysis. Gravimetric analysis because as you let gravity work its course, your precipitate will slowly settle to the bottom of your beaker or test tube or flask, whatever it is you're working with. Once your solid has settled to the bottom, you can siphon off your liquid and get a mass measurement for how much precipitate is actually left or was created through your chemical reaction. So gravimetric analysis, by technical definition, is the analytical technique that predicts the mass of precipitate created based off of the stoichiometry of your reactants. So to get a sense for how gravimetric analysis works, how these calculations work out, how they come together, we are going to be using the previous equations that we've illustrated, the molecular equation, the net ionic equation, the total ionic equation, to figure out if 12.5 grams of sodium nitrate is dissolved in 100 milliliters of water, and an excess of sodium chloride is added, the question is, what's the mass of your product? Specifically, we want to know what the mass of your precipitate is in grams. So we're going to work through this last problem today together just to get a sense for how this problem is set up. If you're looking for a bit of a challenge, feel free to pause the lecture and see if you can't calculate what the mass of the precipitate is on your own. But if you don't feel like pausing, we can just work through this together, and that's totally fine to do, or totally fine too. Well, gravimetric analysis is a form of stoichiometric calculation. And anytime we're working with stoichiometry, we need a balanced chemical equation. It is necessary because we need to be able to compare the ratios of products to reactants. Well, in this example, we are working with silver nitrate, sodium chloride, and we're trying to figure out what the mass of your precipitate is. If we were not already working with silver nitrate and sodium chloride as we have been doing in lecture, we would have to start from scratch, write out our reactants, illustrate some products assuming a double displacement, balance your equation, and determine solubility of products. Because we have already been working with this example though, I'm just going to go back to box the equation specifically that we are working with to save on a little bit of time. So when it comes to working with gravimetric analysis, using the molecular equation, aka the one that's based off of chemical formula, is going to be the easiest and most straightforward way to perform your calculations. So this is definitely an advantage to the molecular equation form. It is very useful when working through stoichiometric calculations. So I'm going to take this equation and rewrite it on the example slide, just so we don't have to keep going back and forth. So I'm going to take a quick pause to edit and just cut this together. The equation is going to be written in 3, 2, and there it is. Here is our chemical equation. So we have silver nitrate with sodium chloride mixing together, creating some silver chloride solid and sodium nitrate in aqueous form. In our problem, we are asked to find the mass of the precipitate, and a precipitate by definition is a solid product. So we can infer that we are being asked to find the mass of our silver chloride in grams after the two reactants have been mixed. Well, now that we know where we're going, we have to figure out where we're starting from. What is our limiting reactant? Because that's something we always have to keep in mind. Now that we are formally working with chemical equations, we have to always ask ourselves, what is the limiting reactant? Well, in the wording of the problem, we are told that we have 12.5 grams of silver nitrate and an excess of silver chloride. This helps us greatly because it means that we don't have to go through the entire process that we saw in Chapter 8 to determine what our limiting reactant is. We are explicitly told that sodium chloride is the excess reactant. So this means that we are going to be starting with the mass of 12.5 grams of silver nitrate and using stoichiometry to predict how much silver chloride is going to be formed as a result. So I'm gonna switch colors again, just one last time, again, trying to keep some contrast here. So if we start with 12.5 grams of our silver nitrate, here we can kind of drop the aqueous form, since in this type of stoichiometric calculation, the form is sometimes useful for bookkeeping, but it's not explicitly necessary in the calculation itself. We must first get out of the unit of the gram and into what unit? The unit of the mole, right? Anytime we're working with stoichiometry and balanced chemical equations, we need moles. And this is because our stoichiometric coefficients out in front of each of our species is kind of implicitly in the unit of the mole. It's technically in the unit of atom or molecule, but since it is proportional to the mole, we can also kind of implicitly assume it is proportional to the mole as well. So in order to actually perform this stoichiometric calculation, we must first get out of the unit of grams of silver nitrate and get into the unit of the mole. For this, we are going to need to find the molar mass of silver nitrate, which is 169.9 grams per every 1 mole. And here, the next step is going to be formally to get out of the unit of silver nitrate and into the unit of silver chloride. Now, in the balanced equation above, we can see that technically these stoichiometric coefficients present are all 1, so mathematically this step can be skipped. But we're trying to get used to, as we have been this entire semester, using our units. So we must acknowledge that we are getting out of the unit of silver nitrate and into the unit of silver chloride. This process, this attempt at always trying to keep track of where you are in your chemical equation is so useful. It is useful specifically if you are not a very numbers-oriented person. It helps you to keep track of what it is you're actually working with and where you are in the chemical equation. The 12.5 grams pertains to silver nitrate. It has nothing to do with the silver chloride. So we have to make sure that we are converting out of the unit of the silver nitrate and into the unit of the silver chloride. Once we are in the unit of silver chloride, our last but not least step, since we are also out of the unit of the gram and currently in moles, and also out of silver nitrate and in silver chloride, Our last but not least is to get out of the unit of moles silver chloride and into the unit of grams silver chloride. This is going to give us a final mass measurement, a prediction for how much precipitate we would expect to see after this reaction has occurred. So let's find the molar mass of our silver chloride, which, based off of calculation, is going to be 153.3 grams per every 1 mole. This will remove the unit of the mole in our dimensional analysis and introduce the unit of the gram. So upon reacting our silver nitrate with an excess of sodium chloride, we would expect to gather, after the end of this gravimetric analysis, 10.5 grams of silver chloride. Again, it doesn't matter that we have an excess of our sodium chloride. Once the silver nitrate runs out, we cannot create any more silver chloride. So this is going to be the theoretical yield of silver chloride precipitate after this reaction has finished. All right, and that is section 2 in the books. We are just cruising through chapter 9. So here we have some section review problems, first for precipitate reactions, and next for what is being labeled as chemical analysis. These problems specifically have to do with gravimetric analysis. So if you really want to get some good practice in using stoichiometry and predicting how much precipitate product we have, these 2 example problems would be perfect. All right, if you have any homework, please double check and do your homework. But until next time, class is dismissed.